just give you an introduction to us if you haven't heard of us, or maybe you haven't heard of our automation products before. So just a quick introduction there, and then I want to get quickly into what is Industry 4.0 and IoT. We're going to start to dissect some of these buzzwords you've heard flying around. And we're going to full circle. So the goal by the end of this presentation is we're going to identify some of these topics. We're going to go through and explain them to you. And then we want to give you some examples of how you might be able to implement them, and then give you a framework on which you can develop and deploy them, as well as some considerations for the future. Just a brief history of WAGO. I've got a little bit of a timeline here that I like to start with. And I think it's nice because WAGO was actually started in 1951 and was invented around the concept of the spring cage connection. So WAGO held the first patent of a spring cage connection back in 1951, and the WAGO story began. So in 1974, WAGO invented the junction box connector, and in 1977, the cage clamp actually revolutionized the electrical connection technology for the spring. So this is kind of the spring cage connection that everybody knows and loves today. In 1995, it was actually our first entry into the automation technology market. So we actually invented the Slice IO in an effort to make more of a modular electronic style terminal block. From there, that remote IO system, we actually decided we were going to develop a PLC system to complement all of this IO that we had. In 2003, that's when we had first invented the push-in cage clamp, and that's something that's more standard in the industry today. Is if you've got a ferrule on the end of your stranded conductor, you can directly push it into the terminal block. And beyond that, 2020 and beyond, we've had continued improvements in our automation system. We've got a new line of touch panel HMI PLCs. We've got over 500 different IO modules now, and we've even just released our IO System Advanced, which allows us some hot swappable options, some high-speed IO options. So we're very excited about the future of WAGO and automation. So if you were asking me why some of our customers use WAGO, especially the automation side of things, one of the reasons is because we actually have onboard connectivity options for more than 16 different industrial field bus protocols. So we can even have multiple field bus protocols on one PLC, which is somewhat unique because you can kind of use it as a gateway in that way. We've got IO for harsh environments, including plus 40 to plus 70 degrees Celsius, extra shock and vibration ratings. We have IoT communication capabilities built in, including options for Mqtt and spark plug for ignition Scada, which obviously we're going to be talking about today. We also have security features built in, including a built-in VPN, Tls encryption, and whitelisting and blacklisting options right off of the PLC. We have local technical support and US-based technical support 5 days a week at no cost. So we have local application specialists distributed throughout Canada to help you with your application requirements. And of course, industries that we deal with customers in a multitude of industries, but today we're going to be focused on the manufacturing industry and how we can help generate some efficiencies for you. So what is Industry 4.0 and IIoT? If we look at a historical recap of the 4 industrial revolutions, the first industrial revolution is probably the one you learned about in the textbooks in middle school, and that was the coal and steam revolution. The second one in the 1870s was based a lot around the internal combustion engine and also mass production. The third, starting from the 1970s, was the advent of semiconductor production, electronics, and PLC automation of our lines. Now into the 2000s and beyond, we're talking about things like cloud, cellular networks, big data, machine learning, and that convergence of IT and OT, which we'll talk about. But really, we're talking about the digitalization and smart factory. So IIoT, what does that stand for? It stands for the Industrial Internet of Things. You might have heard IoT before. In this case, we're talking about the Industrial Internet of Things. And I think there are 4 features that define IoT. I mean, you can look up multiple different definitions all over the web, but I think these 4 features were the ones that most define it for me. So the first was intelligent assets that can sense, communicate, and store information about themselves. So we're talking now about, you hold your phone and it's basically a smart computer. We have smart devices everywhere and they're getting smaller and smaller. So in IIoT, we want intelligent devices that can sense, communicate, and store this information. Of course, this is useless if we have nowhere to send that information. So having a public or private data communications infrastructure, especially a cloud, which we'll want to talk about later, allows us to have somewhere to put that data, to do meaningful things with it. And then speaking of doing meaningful things with the data, having the ability to have the analytics and applications that generate business information from the raw data. So it's not enough just to have the data. We need to have the right software tools to be able to analyze, interpret the data, and then make decisions with that data. And then finally, the last feature is people, because we're actually helping to increase their productivity and effectiveness at all levels of the organization, from the plant floor, helping somebody day in and day out complete their tasks, all the way to future planning that the CEO might undertake. So what are 5 characteristics of the smart factory? So I took this quote from Deloitte because I thought it was particularly interesting. The smart factory is a flexible system that can self-optimize performance across a broader network, self-adapt to and learn from new conditions in real or near real time, and autonomously run entire production processes. So that's obviously pretty lofty goals there, but we'll talk about how we can get there. So what is a smart factory? I guess the other thing we should mention here is that a smart factory is really the factory that's utilizing all these IoT technologies to their full potential. So when we talk about smart factory, the 5 characteristics of the smart factory be connected. So we want to have real-time data collection and over-the-air updates. It needs to be optimized. We're trying to improve uptime, and we want to make things as automated as possible, whether on the production floor or for business decisions. We want things to be transparent. We want live metrics so that we can enable fast decision making. We want things to be proactive. We want to be able to predict failures. It's not enough to have something fail and then send somebody out at that point. We want to be able to figure these types of issues out ahead of time. We also want it to be agile. So we want to be able to add or remove nodes without impacting the existing infrastructure. So the items that we have highlighted in green, these are capabilities that are provided by the operations technology or OT side of the business. So traditionally, these are departments including engineering, maintenance, manufacturing operations. They're traditionally working with technologies like PLCs and Scada. The items in black are the capabilities provided from the IT side of the business. So this includes departments like management, accounting, technologies like our ERP system. So when we talk about OT and IT convergence, this is being able to combine these capabilities to improve all aspects of the business. So what innovations make IoT feasible? So we're going to have 4 pillars here, and the first pillar is going to be systems on chips. So chip technically a system on chips typically includes a CPU, memory, some type of networking, via GPU, other peripherals all in one small package. And I specifically mentioned ARM here. You might have heard ARM recently in the news as NVIDIA's been trying to buy them to enter the CPU market. I mentioned ARM here not only because we use those processors in our WAGO PLCs and HMIs, but because these processors are especially powerful for a small footprint and a low power consumption, which makes them ideal for an IoT application. So for remote applications around the plant, maybe we don't have a lot of power available, so that's ideal. And also the size is also ideal. If you haven't heard of Moore's Law, this is also it's not really a law, but it's more like a principle that's helping to revolutionize the IoT market. So Moore's Law states that the number of transistors on an integrated circuit doubles about every 2 years. If you look at this graph, it doesn't really show that, right? It's looking linear, but actually there's an exponential growth because we're looking at this from a logarithmic scale. So we're getting an exponential growth on the number of transistors we can have on an integrated circuit. Why does that matter? Well, now we've been able to take those processing units, make them smaller and smaller and smaller. So now that we have these smart devices distributed throughout the facility that are able to not only gather the data, but make decisions with the data or precondition the data before we send it to a cloud or some type of other database. So the ability to make these machines smarter and smaller, whether it's a smart sensor or it's a PLC, is crucial. Open source software. So if you're not familiar with open source software, it's free software. It's a type of computer software in which the source code is provided to study, change, and distribute to anyone for any purpose. So Linux is an operating system that's particularly important because of its stability and its low system resources. So if you're thinking for something like an IoT application, an application-specific processing, we would call it application-specific processing, there's no need for a full-blown graphical user interface like Windows. Okay, this thing is computing one task and it's trying to do it well. It doesn't need all of the extra fluff there. So as we can see below, from this graph below, 71.8% of IoT devices are running on Linux. Okay, that's substantial. Now I've mentioned Python here. Obviously that's a programming language, but it's a particularly useful one for using machine learning tools like TensorFlow or machine vision with OpenCV. It also has tons of other uses for data analysis. So GitHub is both a tool for software development and a community for users to post development code about open source projects. And really, the community aspect is what's most important here. People are able to post clips of their code for other people to use and repurpose for their own. So there's a lot of sharing in this open source community, of which people can use other people's code and repurpose it for their own use. Another type of another software I'd like to mention here is Node-RED, and I think Node-RED is interesting because it's an open source programming environment that allows for a simple drag and drop programming of a PLC. Now, Node-RED is still very much in its early development and early versions, but it's becoming stronger and more stable, and it's going to keep growing and will likely start to replace traditional forms of programming because it is so simple. Broadband, Wi-Fi, and cellular. So in 2011, the 4G cellular networks brought fast and low-cost data plans to the market. You can think this is about the time that they released the iPhone 4. Everybody started getting an iPhone, and the need for data was starting to increase because more people found the benefits of what they could do with these handheld computers. So you can see here from the graph that 2011 timeframe was when the price per kilobyte of data starts to really decrease. The internet itself, the expansion of the internet's infrastructure, contributed to greater supply to meet this new demand of all of these systems that we had on the internet, including our phones and other devices. So you can see from the graph on the right here that back in dial-up days, costs were pretty expensive and the bandwidth was quite low, it was quite slow. Now today, obviously, we have high-speed internet and the cost is much lower. So it's enabling us to capture more data for a less expensive cost. And then I'm sure everybody has one of these in their house, wireless router and Wi-Fi. So basically now it's easy to get devices onto the internet without having to run Ethernet cables to everything. Obviously, you don't run an Ethernet cable to your phone to connect to the internet. Basically, this reduced cost. And if you want to think about it in an industrial standpoint, you don't have to run Ethernet cables and switches around your facility. If you have Wi-Fi, it can reduce your cost, and it also speeds up your deployment because you don't have to plug these things in. Cloud services. So if you're not familiar with the cloud, cloud is a model of computing where servers, networks, storage, development tools, even applications or apps are enabled through the internet. Basically, it's somebody that has a bunch of servers sitting at some geographical location and is hosting all of this stuff remotely for you. So instead of having a local server at your industrial site, you're now getting somebody else to house these servers for you. And the benefit of that is there's no local hardware for you. So you don't have any hardware costs. Basically, the service provider owns those servers. It also eliminates maintenance and possible downtime of these local servers. So another thing that you don't have to worry about. And the nice thing about it is the onboarding is quickly scalable for multiple devices and is much faster than deployment on a local area network. And this is one of the things we talk about when we talk about IoT, and what we're going to talk about soon is the scalability and the availability to quickly scale up the amount of data you're collecting to make better decisions. So when we look at the number of devices, the Internet of Everything, it's only going to increase and increase. And especially at your facility, you can start from a small number of devices, and then as you have a need for more data, you can quickly scale up to more devices using something like a cloud. Now, of course, internet security is one of these questions that comes up a lot with cloud. TLS encryption is now widely used across the internet. In fact, our WAGO PLC has built-in TLS encryption. So TLS encryption is one method of securing data over the internet. But Amazon Web Services, for instance, generates all of their security certificates for which to connect. So you get a security certificate to them for each device. Amazon Web Services also offers an entire suite of security, identity, and compliance services. And I'm sure a lot of these other cloud providers too. So if data security is important to you, that is something you can definitely look into and you can try to mitigate. So basically, IoT, IoT is not a fad. It's only going to increase as new technologies developed. If we look at 5G, 5G will enable more bandwidth to send more data. Starlink by SpaceX will basically allow data transfer anywhere around the globe, even in the most remote areas. Augmented reality will help people implement decision making in real time. And AI, such as machine learning, like we're going to talk about, is enabling automated decision making better. It's enabling the automated decision making, and it's enabling us to make better decisions that it wasn't before possible. So why IoT? So if we look at some of the existing systems from Industry 3.0, we'll call it, traditionally there have been many sophisticated systems. I mean, these weren't dumb systems. We had MRP, we had ERP, we had Scada, we had PLC and DCS. We had different types of CNC and machine-specific protocols around the plant. So I would say that we actually have the tools right now to make and deliver our products effectively and efficiently. So we're able to maximize throughput, minimize waste, focusing on quality metrics, and on-time delivery with MRP. The problem is that these systems weren't always properly connected or were difficult to connect. There was no simple way to have an integrated dashboard with multiple linked metrics. Further to that, the software automation was not sophisticated enough to make important decisions without human intervention. So really, when we go back to the definition of smart factory, we're talking about automated decision making or helping with the automated decision making process. So when we look at IoT outcomes we hope to accomplish in manufacturing, there are various areas throughout the value chain from design to aftermarket service that can be improved. So some of these improvements that can use the WAGO PLC as a tool include facility optimization and improvement. So basically looking at utilizing specific benchmarks to determine an issue with the process, including alarms, specific limits, basically if we want to save energy and reduce our costs. Condition-based maintenance alerts. So we maybe want to optimize our machine availability by knowing when maintenance is required and then automatically scheduling that through our ERP system. So if our ERP system is on the cloud and we have the communication ability to send that data back and forth efficiently and make decisions, let's say we know that a machine is going to go down because we have that predictive diagnostic on it. Now we can the information to our ERP to better schedule our maintenance team to come out, thereby potentially reducing the downtime of the machine or better scheduling it. Product improvement through data analysis. So once we get to the customer site, doing quality monitoring and enhancement of products by customer-driven data. So we're looking at how the customer is actually using the product that we've built for them, collecting data and figuring out failure modes of how we can improve it for the future. And then simplifying at the field service level, simplifying that whole deployment by troubleshooting remotely. Now we're gathering all of this data in the products at the field level. So that's giving us a better picture of what issues there might be without having to send a field service person out to actually help them. So now we can do more troubleshooting remotely without having the added cost of sending out. So one of the questions I get a lot is, how does IoT compare to Scada? If you're not familiar with Scada, that's supervisory control and data acquisition. So this is generally a high-level process supervisory management. It's consisting of a lot of computers. We're going to have a lot of maybe some industrial controls on the network. If we look at the diagram, you can see we might have some different industrial field bus protocols, including Ethernet IP, Modbus TCP, all this information coming back to some type of server on site, where then we're actually creating alarms and visualizations. You can see we've got an operator there that might be sitting in control room, checking for alarms, making sure that everything is at the levels it's supposed to be, and where there's alarms, making that known so that the operators can do something about it. So once an alarm event has been detected, one or more actions are taken. We have the activation of alarm indicators for the graphical user interface, such as the operator at the station, or the generation of email or text messages to the operator so that they know to go out to site to fix something. So really it's focused on this alarming and visualization potential. So the pros is that it's an established technology, it's widely compatible. Some of the cons can be that it can be quite labor intensive, especially if you have to have your own server hardware, it can be difficult to scale. So when we look at the industrial Internet of Things, The diagram starting from the left, again, we have our industrial controllers there that might be doing some automation, some different types of plant automation. Again, we're talking these industrial protocols. So Ethernet IP, Modbus TCP, sending it back this time to an IoT gateway. And you can see here that we haven't completely eliminated our Scada. Our Scada still could exist there. So we could integrate our Scada into this control scheme, or we could develop our own Scada, or use a newer type of cloud-based Scada, such as Ignition or something like that. So in this case, maybe we still have our we still have our Scada integrated, but we're sending all this information back to an IoT gateway, then sending it to the cloud. And then from the cloud, we can send it to a variety of different cloud services, such as an ERP. Maybe we want to do some machine learning because we've got some predictive diagnostics. We still want to send notifications, just like we would from our Scada. So we've got an option for that, and maybe some high-level dashboarding as well for management. So again, this is scalable by design. We're using that cloud-based model, so we're per kilobyte of data. It allows us the ability to quickly online a number of devices, whether it's IoT gateways or smart sensors, onto these servers without having to buy and maintain the servers yourself. So this leverages the ability to put the data into a widely understandable format, such as JSON, to connect to other platforms. And JSON is a data interchange type that we're going to talk about later. Gains the benefit of tools widely available in the software development industry for data analysis and decision making. So of course, one of the important factors of all of this is gathering the data, but then making the right decisions. So you do have to have the right people that know not only how to interpret the data, understand the data, but being able to derive the right conclusions from the data. So some of the pros of this system is that it can be less expensive. There can be fewer parts or more parts, depending on how you look at it. It is quite scalable, and there's a ton of new capabilities that we're looking at. Some of the cons, of course, is that there is a learning curve to this. And as we said with the data science, chances are you might need a data scientist or somebody with that type of expertise to be able to come up with the kind of conclusions that you want to get from your data. So there is maybe from a hiring perspective, there is a spot there where you might want to fill that gap. So how do I put IoT into action? Just to give you an introduction to our WAGO PFCs, we actually call them programmable function controllers, not a programmable logic controller, even though I will a number of times call them a PLC. They do a lot more than just a PLC, so we like to call them a PFC. And why is that? Well, the nice thing about the WAGO PLC is it essentially is a microcontroller with an I/O system that can host a number of services. Okay, it runs a host operating system, which is Linux, and we could use a system like Docker to host multiple services right on the Linux operating system. So we could do a lot of things right on board that controller, and that's when people talk about an edge device. That's something that's sitting on the edge of our IoT network that's maybe either preconditioning the data or doing some calculations outside of the cloud. So maybe we want to do some data analysis and calculation before we even send that information to the cloud. We can do that right off of this edge device. So some of the benefits of this is, again, the computations can be done independent of the cloud. So there's no need to infer that data transfer cost. Also, as we said, data can be pre-processed, and I'll have an example later on that shows you, should give you a good example of this. And of course, we can run this as an IoT gateway in addition to a PLC. It still has options to trigger inputs and outputs, and it also has, you can see in this example with the IO buses there, we can still, or the field buses there, we can still actually talk to multiple industrial field buses. So now, apart from the controller, if we want to send data to the cloud or we want to send it from the cloud to other cloud services, one aspect that's important here is the data interchange format. So how are we sending the data? What type of data are we sending so that everybody can understand it? And JSON is actually, it's short for JavaScript Object Notation. And in the quote on the right here, it says, today, when any two applications communicate with each other across the internet, odds are they're doing so using JSON. Okay, so that's fairly significant. So what is JSON and what is a JSON API? Well, a JSON API is basically a tool that uses JSON, and it's designed to simplify communication between servers and applications. So an example of this is actually within our WAGO programming environment called eCockpit. We can take variables and we can transform this to this IoT JSON data type. For example, you can see on the left here, I've got something in the some items here that I wanted to transfer to a JSON object, JavaScript object notation. So I've done that here on the left. But basically what I want to do is I want to move my variables and I want to move my information from the eCockpit environment. I'm going to convert it to a JSON data type. Then I can easily send it to the cloud, so for instance, Amazon Web Services, or maybe from Amazon Web Services, I need to do some data science with it. I need to actually manipulate and analyze the data. I can send it to Python and other numerical analysis tools. So the nice thing about this, again, is that it uses a consistent data model that is also human readable compared to some other markup languages like XML. And I don't know if you've ever accidentally opened an XML file, but there's not a lot that's human readable about that. So what are some of the advantages of JSON over traditional like HTTP based protocol? And really it's that it reduces both the number of requests and the amount of data that's transferred between clients and servers. So it's a lot more efficient, and especially when you have multiple devices on this network, we want to make sure that we make it efficient, that we're using our bandwidth as efficiently as possible. So a good example of this is actually Mqtt. Mqtt is machine-to-machine Internet of Things connectivity protocol, and it's actually one of the best known protocols for cloud IoT. The advantage of it is that it's lightweight and it scales very well. Of course, it also uses JavaScript object notation. So in this example, you can see I've got a diagram, right? And basically what I'm doing here is I'm generating some information from site 1, and I want to send it to a database, maybe site 2, maybe site 3, various other sites. So instead of other protocols where I might need to manage a list of addresses that the data needs to be sent to, in this case, at site 1, I can simply publish that topic for whatever information I want to send, and the other devices can simply subscribe to it. So that's what we call a publish and subscribe model. So in this case, if we look at the information on the left-hand side here, basically I've set up my topic called pressure. My value is 125. I know that it's an integer. Okay, so site 1 publishes this topic. I have my database subscribing to it. Site 1, site 2, site 3, site 4, all subscribing to this. So you can picture that in a plant environment, when I want to start onboarding a lot of different types of smart devices, they can simply publish and subscribe topics to each other very quickly and efficiently, which makes this whole process a lot more scalable. So what's an IoT example using WAGO? So here we're going to look at power measurement and monitoring. And the goal of an IoT approach is to really generate long-term real-time data and to use a descriptive analytics process to provide a big picture, basically a big picture about energy consumption. And this can include alarms regarding potential instabilities or issues with the facility, but it could also include just overall strategies for cost savings, right? So if we look at the diagram on the left here at the device layer, so this is the hardware level, I've got multiple PLCs, maybe WAGO PFCs located throughout the facility with some power measurement modules. So we might be measuring power at different spots in the facility or different lines to better understand, get some data, and do some predictive diagnostics here. So we're running WAGO and we're running the eCockpit programming environment. At the communication layer, we're using wireless LAN. And in this case, we're using Mqtt. At the data layer, this could be our server on site, or it could be our cloud-based server. In this case, we're going to assume that it's a cloud-based server just because we like the scalability of it. Now, I did put the Mqtt broker there, but that's something that helps the publish and subscribe. But that could actually sit right on the WAGO device. Then at the information layer, we're actually taking a lot of this data from the cloud and sending it to do either predictive analytics through Python or some of the other services available, or we're sending it to a dashboard for information to be shown. And it could be going back and forth. So let's look at some different problems and figure out some different requirements on how we can implement IoT. So problem, pattern identification to check problem hardware deviations and abnormalities. So let's say, for example, you had a particular process in compressed air that's showing more power consumption than usual. This can help you quickly identify that your compressor may be leaking or there's some type of mechanical blockage that is causing the compressor to work harder or something. So real-time monitoring and the graphical as well as the predictive alarms really helps us get there. So in this case, we could use Grafana to display some database queries from InfluxDB and Python for data science and analysis. The next problem is the network infrastructure, such as Wi-Fi, can have multiple connection interference issues causing signal interruptions. And this is could be quite common for an industrial plant environment. I mean, you might have a lot of EMC going on. Your Wi-Fi might not extend as well as you thought it did, so you're getting some latency issues. But if you use Mqtt paired with a properly configured broker, such as Mqtt, to help reduce the, you can actually reduce the latency. Sorry, to reduce message latency and lost messages, while also taking advantage of the keep alive function. Basically, what I'm trying to say here is if you are running into latency issues, you can actually set an importance on what types of data are going to be more important than others. And also, if you are losing messages, you can choose that, okay, I want to make sure that I get this important data rather than the less important data. Now, in a case where you don't want to lose any data, you can simply turn off that connection and use the keep alive function. So, if you did lose the connection is not just going to time out. The keep alive will keep it alive until that connection reestablishes, and then it's able to send the information. So that's another key part of it. Again, you can also use something called Sparkplug, which is a protocol buffer version of MQTT, and it could be considered based on the instability of the network. So the next problem we have is maybe standard IoT sensors won't convert the current and voltage data to other types of power data, such as harmonics and reactive power. So in this case, we're using a WAGO PFC. We've got a power measurement module. We're connected to some CTs and some VTs. We're actually able to maybe process the data from the bits and bytes that we're getting in from the CTs and VTs, turn it into voltage and current data, send it via JSON, MQTT, to the cloud. Now we have data in a format that makes sense. Another problem, data format is not standard across energy monitoring solutions like HVAC protocols and lighting protocols. So if we use something like MQTT, again, paired with the WAGO PLC to act as an Iot Gateway, we can actually act as a gateway between other communication protocols. So we can bring this information in through BACnet, DALI, whatever protocols that we're using, and we can convert it through MQTT cloud-based protocol, so that now we can send it to the cloud and do some data analysis with it. So deployment and development considerations. I've got 4 categories here, starting with upgrading existing equipment and processes. We've got our IoT gateway. How do we choose that? How do we choose our cloud platform? And how do we choose our UI and dashboard? So when we're looking at our requirements, when we're upgrading our existing equipment, what type of protocols is the equipment currently talking? What kind of I/O do we have there? And is it in any kind of IP67 environment, cold environment? What do we have going on there? So some questions to consider are, maybe we want to come up with a list of machine parameters that we want to monitor. So what types of sensors will we need to monitor those parameters, and how frequently do we need the data? How many systems are we going to need, and what's the cost associated with that? From a cloud platform standpoint, obviously, do we want to use a cloud platform? If we are we going to use a cloud protocol? Do we want to use machine learning? What's the cost associated? So again, what is the data going to be used for? This is where we really want to nail down what kind of decisions are we going to drive with this data? For an IoT gateway, we might want to decide, okay, what type of industrial protocol are at the machine that we need to convert with our IoT gateway. And then in terms of deployment, are there any network considerations that we need to take into account? Is there Wi-Fi available? Do we need to send this stuff over wired Ethernet? Are there cybersecurity concerns, etc.? You might also want to look at what programming language you're using. For instance, if you are preconditioning the data and you did want to use a WAGO PLC for that. And UI and dashboard, obviously we want to figure out what our visualization requirements are, who's looking at it. We can set up alarming and notification, maybe some manual entry for operations. Questions to consider is who's going to develop these screens? Do we need any web integrations, and is there a Scada integration? So basically in review, by taking these 4 categories into consideration, we can start finding ways to implement IoT in a manufacturing environment and move towards self-optimization and more automated, better quality decision-making.